This video, we're going to be talking about sigma notation, how we can find sums of a bunch of different numbers here. Before we get into that, in case you missed class today, I want to talk about the warm-up because the warm-up kind of led us into what sigma notation represents and a pattern which we can use and a concept which applies to our sigma notation. So we're going to do this one first. First, we want to find the sum of integers from 1 to 5. So we're adding 1 plus 2 plus 3 plus 4 plus 5, which we could do pretty easily and figure out that's 15. But eventually, when we start adding numbers in between like 1 and 50 or 1 and 100, that can get a little taxing to do, and we don't want to have to write that all out. So we're going to try and come up with patterns that we can use to help us. So to add all the numbers between 1 and 5, while it may make sense to do it in order, if we actually think about adding things in a different order, we can come up with a pattern here. I'm going to add a 0 term in here just because I want to pair up two numbers. And if I have an odd number of terms here, I don't have an even number of pairs. And so I'm just going to add that 0 in so that when I pair up my numbers, I have an even number of pairs. Adding 0 isn't going to change our sum, so that's okay. So if I add in a different way here, if I just add the first and the last numbers and work inside, then 0 and 5 gives me a sum of 5. 1 plus 4 gives me a sum of 5, and 2 plus 3 gives me a sum of 5. So I have 3 pairs of numbers, each adding up to 5. So that's the same as 3 times 5, which is also 15. Let's try that pattern on the next one. This time I'm going to just organize it slightly different. Rather than writing it linearly, I guess, I'm going to stack my numbers. I'm going to stack the first and the last number and work my way in. So adding 1 and 10 here gives me a sum of 11. If I add the next two numbers, 2 and 9 together, I also get a sum of 11. If I add the next two numbers, 3 and 8 together, I also get 11. Adding the next two numbers, 4 and 7, and 5 and 6, each gives me a sum of 11. Notice that each pair gave me the same sum. So now I can use multiplication instead of adding. I can say that I have 5 pairs of numbers, each adding up to 11. So 5 times 11 is 55, which is the same thing you get if you add these all up together. All right, let's see if we can use that pattern now and stop combining our numbers and having to write them out. So essentially what we're doing is we're adding the first and the last number in our interval, and we're determining how many pairs we can make given the total number of terms in our interval. So all of the numbers between 1 and 20, that's 20 different numbers. If I cut that in half, that tells me how many pairs I can make. So I can make 10 pairs of numbers. If I add the first and the last number together, then each of my pairs should add up to 21. And so 10 pairs of 21 is 10 times 21, which gives me a sum of 210. Let's practice that a couple more times. Adding up all the numbers between 1 and 50, well, I have 50 different numbers there. That must mean that I can make 25 pairs. If I add the first and the last term, I'm going to get sums of 51 for each pair. So 25 pairs of 51 gives me a sum of 1,275. One more time, and then we'll write our equation for this pattern. Adding up all the numbers between 1 and 100, we know that we can make 50 pairs. Each of those pairs are going to add up to be 101. So 50 times 101 is 5,050. So to find the sum of integers between 1 and any number, essentially is just taking the number of terms, divided in half, gives you the number of pairs. And your total number plus 1 is going to tell you the sum of each of those pairs. Another way to think about it, if we are not going in between 1 and a number, is to say that I have half as many numbers in my interval, that's the number of pairs, and if I add the first and the last term in my interval, even if I'm not starting from 1, that will be the sum of each pair. And so really, all I'm doing is the number of pairs times the sum of each pair, and you get the sum by adding the first and last term in your series. All right, so now let's get into sigma notation. So this is where sigma notation comes from. We use this sigma notation to represent sums of numbers, or a sum of all the outputs of a function if we start to include a function here. In the notation, on the bottom of that sigma, you're going to have a variable equaling a number, and that's going to be your starting number. It's called the index of summation. So the number below is always going to be what number you start with in your interval. Above the sigma symbol, you're going to have another number. That's the ending value. That's the number we're going to count up to. And then just to the right of that is going to be some function, this being the most basic function right here. So this means that I'm going to plug in 1, 2, 3, and 4. I'm going to count from 1 to 4 and plug them into that function. Since there's no math going on with that function, I'm just adding the integers as I count up. So I'm adding all of the integers between 1 and 4 in that case. Sometimes the variable letter can change. As long as the variable in your index matches the variable in your equation, doesn't matter what letter we're using. So here we got an index starting at 1, or our interval is starting at 1, and it's counting up to 3. And we're just going to do a little linear function here. So we're just going to plug in 1, 2, and 3 and add them together. So adding the outputs of that function by plugging in numbers from 1 to 3. Next, the function gets a little bit more complicated. Now we have a square function here. So now I'm going to add up all of the squares from 1 to 4. So 1 squared plus 2 squared plus 3 squared plus 4 squared. That's going to give us a sum of 30. There are some properties we can use with sigma. Sometimes they help us simplify things. Other times they may be more complicated than what we need. Well, let's talk about them. First thing is we have a constant rule, and this is kind of one of the more complicated ones, or harder to understand. It's a little weird that we're not plugging numbers in anymore because we don't have a function. So we just have this constant number. So in this case, it's kind of a special case. This is saying I'm not plugging numbers from 1 to 3 into 2. That doesn't make any sense. What you're doing is you're just adding 2 to itself the amount of times that is the length of your interval. So from 1 to 3, that's 3 spots in our interval. So I'm going to add 2 to itself 3 times. So 2 plus 2 plus 2 is 6. And then this rule is giving us a little shortcut. If we start at 1, we can use this shortcut. All it's saying is that another way we could do this is just multiply that constant number by your ending number, which would be 2 times 3. That would still give us 6. All right, sometimes we have more than one term in our function, so some sort of polynomial, something with multiple terms. In that case, terms that are being added or subtracted can each get separated and be given their own sigma. So one way to think about it is to distribute that sigma to each term. So for example, if we have the function I plus 2, I could break that up into 2 terms and find the sum of the function I from 1 to 3 and the sum of the constant 2 given an interval of 3 there. So if I plug 1 into this function, 1 plus 2 plus 3, counting up to 3, I get 6. If I add 2 to itself 3 times, given the length of our interval, I get 2 plus 2 plus 2, so we got 6 plus 6 here equaling 12. If your function has a coefficient or a number in front of your variable, then we can use this coefficient rule, which just says that we can move the coefficient out to the front and treat it like a multiplier, and find the sum of the function first, and then just multiply it back with that coefficient. So if I shift my 2 out to the front and then evaluate my linear function from 1 to 3, plugging in 1, 2, and 3, the sum of 1, 2, and 3 is 6. If I double that, bringing that 2 back in to distribute, 2 times 6 is 12. So there's 3 basic rules or properties that you may use to help you. We could get a little bit more complicated, but first let's just focus back on that initial basic sum function of just a linear function. So that brings us back to here, our warm-up. That's just essentially what we said right here. Anytime we're just finding the sum of a linear function, we're thinking about that concept of taking the number of pairs in our interval and multiplying it by the sum of your pairs. So the number that we start with and the number that we end with. So this is exactly the same formula that we came up with on our warm-up. If instead we have square functions, rather than plugging values in and squaring them, we could instead use this little cheat formula right here. Plugging in that top number, again, only if we're starting from 1. And then there's also a cube function shortcut. You can write it in this form or square that and write it in that form instead. Either way it works. The reason why we only need these basic linear, square, and cubic functions is all other higher degrees could get broken down into these basic forms. So for example, I to the 5th could be I squared times I cubed, and you can just use those two forms to do it. We're not going to see anything that complicated in this video, but you're welcome to try it out. All right, let's practice finding sums. In this first one, again, we got that basic linear function. So we're going to add up the numbers between 1 and 5. We could do it the long way, or we could use that conceptual shortcut. Our interval is a length of 5. So we know we have 5 divided by 2 number of pairs, so 2.5 pairs. It's kind of weird to think about a half of a pair, which isn't really true, but mathematically it works. Adding the first and the last number in your series or sequence or interval will give us the sum of our pair. So if we have 2.5 pairs and each of our pairs add up to 6, then 2.5 times 6 is 15. All right, in part B, we have 2 terms in our function. So we're going to use that sum and difference rule. We're going to distribute our sigma to each of those terms. So we're going to find the sum from 1 to 4, and then we're going to add this constant term of 1 added to itself 4 times. That's the length of our interval from 1 to 4. So our interval is 4 numbers big or long. Cut that in half, that's the number of pairs. So we have 2 pairs, and each of our pairs are adding up to 5, the first number and the last number in our sequence. So 2 pairs times 5 is 10. Here we have our constant rule. We could say this is 1 4 different times, 1 plus 1 plus 1 plus 1. Or we can use the shortcut and multiply that constant by our last number, so 4 times 1. So we got 10 plus 4 giving us 14 there. All right, part C. This is the first time where we are trying to find the sum of something that doesn't start from 1. So instead, we're going to try and find the sum of numbers between 3 and 7, given the function x plus 1. We could go the long way. It's not too bad if we just plug a 3, a 4, 5, 6, and 7 in. We could add all of that up and get 30. Or we can use our shortcuts. But this time we can't use our formulas because we're not starting with an index of 1. We're starting at 3, so we got to think more conceptually here. Still the same concept though. The length of our interval divided by 2 gives us our number of pairs. So the length of our interval from 3 to 7 is 5. Don't make the mistake and think it's just the difference between those numbers. 3, 4, 5, 6, and 7, that's 5 numbers. So one shortcut that maybe you use besides counting on your hand, maybe find the difference and add 1. That would be the number of numbers in your interval. So 5 numbers in this interval. Divided by 2 gives us the number of pairs, so we know we have 2.5 pairs. Each of our pairs are going to add up to the sum of the first and last term in our sequence here, so 3 plus 7 is 10. So we're going to do 2.5 times 10. That'll evaluate that first sum. Second sum is just a constant, but be careful, don't use the constant rule because we're not starting at 1. It's not going to be 1 times 7 here. It's going to be 1 times the length of our interval. So the length of our interval was 5, so 1 times 5 is 5. So now we got 25 plus 5 giving us 30, the same thing we got when we went the long way. All right, part D, going back to starting at 1. We're going to count from 1 to 5, or plug in numbers from 1 to 5 into the function k squared. So we're going to square or add up all the squares from 1 to 5. So we could write that out and get our value as 55. But we could also use one of these shortcut rules. So looking at the square identity here, plugging in our top number into those end spots. So we're going to have 5 times 5 plus 1 times 2 times 5 plus 1, all divided by 6. Simplify, 5 plus 1 is 6, 2 times 5 is 10, plus 1 is 11. Multiplying by 6 and dividing by 6 will cancel, and so we just have 5 times 11, which is 55. All right, last one, part E. This time we're going to try out a few different properties all in one problem. Usually, before you start to use your summation, you want to combine terms or expand so that you're just looking at individual single terms. So one thing we could do is distribute the 2 and have 2k squared plus 2. Or we could shift that 2 out to the front and then evaluate k squared plus 2 and multiply that 2 back in on the end. Doesn't matter either way. I'm going to distribute the 2 and have the terms 2k squared plus 2. And I should have parentheses around that. Be careful there, because if I had written it this way, that's definitely not what I meant to do. The sigma would only apply to this first term. And so we would be finding the sum of that, and then we would add 2 to that. And that's not what I meant to do, so sorry about that. Put parentheses there. All right, so we got 2 terms. We're going to separate them, distribute that sigma to each term. And since we have a constant in front of that first term, we're going to shift that 2 out to the front of it. So we'll find this sum, the sum of squares from 1 to 3, and we're going to double it. And then we'll find the sum of 2 added to itself 3 times here. Our interval is 3. So using the k squared formula, we got 3 times 3 plus 1 times 2 times 3 plus 1, all divided by 6, and we're going to double it. That 2 is still out in front. Here we got 2 added to itself 3 times. That's the same as 2 times 3. We could do a lot of simplifying here to help us with this multiplication. We have 3 being multiplied, and 6 is our divisor there. So if I'm multiplying by 3 and dividing by 6, we could cancel those with common factors. We could divide them both by 3. And so that 3 is going to go away. This is going to become a 2. And now I'm multiplying by 2 and dividing by 2, so that's all going to go away. So we're just left with 3 plus 1, which is 4, times 2 times 3 plus 1, which is 7. So 4 times 7, plus this 6 right here on the outside. So we got 28 plus 6, that's 34. All right, lastly, we're going to work backwards. Given a description of a sum that we want to find, we're going to write the sigma notation first, and then we're going to evaluate it. So write the sum of the function x squared plus 1, given an interval between 1 and 5. So we'll use our sigma. We're starting on our interval at 1, and we're going up to 5. So we'll have x equals 1 on the bottom, going up to 5 on top. I'm using x as my variable because that's the variable in my function. As long as the variable in your function matches your index variable, then you could use any letter you want. And then we put our function right next to our sigma. So let's evaluate it. We got two terms, so we're going to distribute our sigma to both terms. We have an x squared, or a square function there. So I'm going to use my square function identity. Take that top number, plug it into the end spots. And then here we got our constant. So we can use our constant rule because we're starting at 1. So this is just 1 5 different times. So 5 times 1. Here 5 plus 1 is 6, and 5 times 2 is 10, plus 1 is 11. So here we have 6 being multiplied and divided. We can cancel that. So we got 55 plus 5, and that's going to give us 60. All right, the last one, kind of a little challenge here. What if we no longer want to count by ones? What if, for example, we want to find the sum of even numbers between 2 and 8, so we're counting by 2's? Well, that's easy enough to do without sigma notation, so the challenge comes when we try and use sigma notation. Obviously, we can add 2 plus 4 plus 6 plus 8, and we get 20, so we know what we're trying to get to. But how do we count by 2's? Well, here's what we can do. We can think about this as sub-intervals. So counting by 2's, I go from 0 to 2, and then in my next interval, I'm going to jump from 2 to 4, and then I'm going to jump from 4 to 6, and then I'm going to jump from 6 to 8. So I have 4 different intervals here, and in each interval, I'm changing by 2. So if we use our sigma notation, if I start with my first interval, and I count up 4 intervals, what is my function going to be? Well, we're just going to have a linear function. We're just going to be plugging in the interval number, and we're going to be multiplying by 2 each time. So let's see how that works. If I plug 1 in, I get 2, which is what I wanted to start with. If I plug 2 in, I get 4, so I'm counting by 2's. Plug a 3 in, and 2 times 3 is going to give me 6. Lastly, I'm going to plug my last interval number in, 4. 2 times 4 is 8. So we can see that that allowed us to count by 2's, and now we get the same thing, 20. If you wanted to use one of our properties there to do it instead, take that coefficient out to the front. So now we're plugging in values from 1 to 4 here. So 1 plus 2 plus 3 plus 4, that's 10. And if we double that, we still get 20. So it works either way we do it. It's a bit of a challenge problem. Definitely don't beat yourself up if that was tricky. Be able to do something more like this, and certainly be able to do these types with a focus on part C. Definitely know that conceptual understanding of our summations, and then also be able to use some of those properties or rules to help you. So good luck practicing sigma notation and finding summations.